Hi and welcome to another Hopper internals video. This is a program running on the Arduino RP2040 Nano Connect. It's been running all afternoon. I've just set a breakpoint, so it should stop when it hits this breakpoint after the next time it connects. It's doing web calls, getting some JSON from the web, parsing it, putting it into internal structures, and then pulling out information to calculate the current time of day. And there it just finished that lap. It's doing a lap every 30 seconds. Every 30 seconds it's doing these two web API calls. I've got another video that explains this app. I'll link to that afterwards. The point of this video is to show the memory diagnostic features of Hopper. That's why it's an internals feature. So obviously this debugger can get to, let's switch away from showing that. Yes, here we go. The debugger here has a call stack, and it has local variables that you can examine. So obviously it needs to get this information off the device. So this is currently running on the device. So it pulls this information down from the device via the serial port and displays it in a pretty way that you can, so when you step here, you can see things change when you're in the debugger. But if you want to look at all the memory managed by the runtime, you can dump it to a text file with this dump memory feature. So this will dump, the data segment for the runtime is 64K. And if you want to look for memory leaks or look to see how much memory you've allocated or how the memory is being allocated, how much memory is this program using at any one time, and is it all good? So, or are there leaks, or are you surprised that something's using too much memory? So let's have a look. So we dump the memory. Bottom of the screen it says completed. Easiest way to look at it is in text editor. So yeah, if it text editor, there's not much dumped here, so it's not that interesting. I'll pause the video and then continue again when I'm just on the next lap, so in about 30 seconds from now, and then we'll see more stuff. Okay, and pause the video. We're about to, there we go. We did another lap, did another 2 web requests, and ended up on my breakpoint again. And it's a lot more interesting when you see all this stuff here. So now with this function here, what we saw earlier was that there wasn't much memory in use. When we were outside this function, there were only 86 bytes total in use, of which only 16 bytes were actually on the stack. So when we're sitting in this method, before we exit the method, before we pop all this off the stack, there should be quite a lot of memory in use. So let's have a look. Let's dump it in this, while we're in this position where we have so much stuff here. So we'll dump that, switch back, and yeah, we've got a lot more memory now. So we've got all these dictionaries, these hierarchical data structures and the dictionaries are key value dictionaries, so they have a K and a V, and the key is a string, and most of the values are strings as well. Some of the values are not strings, like this one's a number, that one's a number. Let's see what else we got in here. Yeah, a value that's a number. So we've got 2 dictionaries. One was for the sunrise, and the other one was for the time. This one was for the time, and they've got a lot of fields in them. And each field, we can see strings seem to be a multiple of 16, which is true. The allocator rounds up the size of a string to the nearest multiple of 16. And this allows for quicker allocation because there's less fragmentation. And it also allows for quicker modification of a string. If you keep appending characters to a string, it only does a reallocation every 16 characters. Right, so now we have a lot more than 16 bytes on the stack. So if we look at the total at the bottom of this column, we've got almost 5K on the stack in this function. And the stack, it is the stack because this is the stack pointer here. It goes up in increments of 2 because they're 2 byte stack slots. So you can see they're going down to 0 here. See, so this is the stack, and it's a garbage collected managed heap where, since it's single threaded by design, if you can't walk to an object via the stack, then it shouldn't. Then it should be collected by the garbage collector. So this is a trivial live list for a garbage collector. So this is the live list for the garbage collector, is the stack. And that is how it works. And you can see every byte and how much is being used by your program. So when you have small devices and you have a limited amount of memory, this is exactly the same for when it's on the 6502 or on the Z80. It uses exactly the same architecture. So you can examine the memory use in exactly the same way. Anyway, let's switch back to our device. And let's get rid of our breakpoint and let it keep running. Because it's been running all afternoon and I wanted to see if there were memory leaks. There aren't any, which is a good sign. So my recently written JSON serialization, string to structures and structure to string, obviously doesn't leave any bits lying around. But it's very hard to have memory leaks in a managed environment. Anyway, thank you for watching. I look forward to your feedback. And let me know if you have questions.